Hello, everybody. I'm Marissa.
My name's Sonia.
I'm Jay.
I'm Monty.
And I'm Brandon.
And our research project is on changing the capping ligand to observe ferrofluid properties.
So to start us, wrong slideshow. So to start us off, let me explain what a ferrofluid is. So ferrofluids are fluids that contain 10 nanometer thick magnetite particles that are suspended in a liquid such as water or oil. Now 10 nanometer thick basically just means that it's super, super, super small particles. So these ferrofluids will magnetize in the presence of a magnetic field, and therefore they are attracted to magnets. As you can see in that picture right there, that is a ferrofluid that is in the presence of a magnet, which causes it to spike. So a couple of current applications for ferrofluids that are being used are in medicine, cooling speakers, lubrication, and rotary seals.
So as Brandon said, these nanoparticles are super, super small. So what we have to do is we have to cap them in order to preserve their nanoparticle properties. And so to do this, we use a capping ligand that is either polar or nonpolar in order to control the nanoparticle growth. So the two different capping ligands that we were using were one that was nonpolar and one that was polar. So a lot of us are familiar with the concept that like attracts like or like dissolves like, which is similar to what we used in our experiment, just like how oil and water don't mix, nonpolar and polar substances do not mix. So we were testing the properties of these two different types of capping ligands.
So our research question is, would altering the capping ligand of a ferrofluid change its properties? We tested this by testing ferrofluid as a lubricant and testing ferrofluid as a filter.
So, since we have two experiments, we have two hypotheses. Our first one for the lubrication is that when we use oleic acid as a capping ligand, the commercial ferrofluid will work more as a better lubricant. And for our second hypothesis, if the capping ligand is oleic acid, the ferrofluid will only interact with nonpolar substances, and if it's mercaptopropionic acid, it will only interact with polar ones.
All right, so the impact of our research is our research will show us if changing the capping ligand. Our research will show us if changing the capping ligand changes which substances, like ferrofluids, interact with. This can be utilized when ferrofluid is a lubricant because we'll know which either polar or nonpolar ligands will work better for lubrication and reducing friction. This can also be utilized to separate polar substances from nonpolar substances like oil and water.
So for our first experiment, we tested ferrofluid as a lubricant on various surfaces.
So the general gist of our first experiment is that we used two different ferrofluids, a water-based one that we made ourselves and a commercial one that we bought online. And we used a control with no ferrofluid. And so what we did is we slid it down a ramp right there, as you can see up there, and recorded the time it took to go down the ramp. The ramp was 1 foot long, and we divided that 1 foot by the time it took to find the velocity and compared those. We have a constant force applied to the block, or applied to the cube sliding down being gravity, so it was there was little error in that regard.
So as you can see on our graph, for our control, where we did not put any lubricant on the magnet at all, the times vary wildly because it would do things like roll because there was no way of it sticking down. But for the water-based and oil-based lubricants, you can see that the times were much more consistent. But you can also see that the water-based lubricants were much worse in terms of reducing friction than the commercial ones. Two possible explanations for this is we made the water-based lubricant ourselves, so it may not have been as high quality as the oil ones, but also the magnetite nanoparticles fell out of suspension much easier in the water-based one than they did in the oil-based one.
As you can see right here, what we did to find the velocities is we took the average of the times and then divided that by the distance. And as you can see, the commercial ferrofluid went down much faster and had a velocity of 0.625 meters per second.
So here are some errors, some lessons and improvements for future experiments with ferrofluids. So as you can see in this picture with the purple glove, we have our magnet coated with ferrofluid. However, this ferrofluid had already dried up, and so in future experiments, we would like to make our ferrofluid with a substance, a suspension fluid that would not evaporate as quickly. In our experiment, we use hexanes, but in commercial products, they typically use things like kerosenes to make it so that it would not evaporate as quickly. And this picture shows a comparison of our ferrofluid versus the commercial product. Now, another error is shown in this ramp. As you can see here, we have our ferrofluid dried on the ramp. Now, this interacted with our magnets as they were falling down, and it caused inconsistencies in their actual speed as they're going down. To combat this, we would use new sheets of foil on the tracks after each trial.
So our second experiment was testing how polar and nonpolar ferrofluids interact with oil and water in terms of separating the two.
So in this experiment, we took a petri dish and mixed oil and some water. We dyed the water red so you'd be able to see. And we basically used our 3-mercaptopropionic acid, which was our polar ligand. And then we placed the magnet under the petri dish. And as you can see in the image, it's pulling the water along with it and the oil is left behind.
So then we used oleic acid as our capping ligand, and this ligand is nonpolar. So we dyed the water green in this test, and when the ferrofluid was added to the oil-water mixture this time, it was clear that the ferrofluid and the oil aggregated towards the center of the petri dish, and the water separated itself around the oil and the ferrofluid.
And although there were interactions between the different ferrofluids and their respective substances, the magnetic nanoparticles were not able to completely separate the two substances. They could only drag some of it with it. So they did not bind enough with the molecules to drag it, causing some oil to escape, which you can see up there. And in the future, we would like to run more tests along these with these substances, along with different ones to see what kind of interactions can be made. And we would also like to test these same interactions at a larger scale so they would have more real-world applications and to see if they would still work at that scale.
So through these experiments, we learned that changing the capping ligand does in fact change the ferrofluid properties. In experiment 1, when we used oleic acid, the nonpolar ligand, the ferrofluid served as a more effective lubricant for the magnet. In experiment 2, we learned that the nonpolar and polar capping ligands are shown to interact with their respective substances.
So in our first experiment, we tested ferrofluid as a lubrication. So here are some future applications for ferrofluids. We could use ferrofluids in industrial machinery as a lubrication, as it is shown to be very good at lubricating surfaces. Now, we could also use it for possibly more efficient transportation in trains and cable cars. So the ferrofluid as a lubricant would reduce the friction of your train or cable car, which would cause it to move faster and require less energy to run. Now, our third application for ferrofluid will be in permanent magnet motors. So as you can see in this diagram right here, the permanent magnet motor is made of a rotor and a stator. The rotor is made of many different permanent magnets, and the stator emits magnetic field that interacts with that field of the magnet in the rotor and causes it to spin. So ferrofluids will be used here as a way of lubricating it to make it go faster, as well as a way to reduce the air gap between the rotor and the stator, which would reduce the loss in magnetic flux with the rotor and the stator and make it overall run more efficiently.
Okay, so possible future applications for our oil, ferrofluid, and water separation is we could separate oil from water in oil spills in order to use a nonpolar ferrofluid to take the oil out of the water, or vice versa in an engine where water has gotten into the engine and we need to remove it without removing the oil. This also has applications for separating different polar and nonpolar substances from each other than oil and water.
All right, thank you for your time. Any questions?
Okay, so you were looking at trying to use these for separating oil and water, and there's a lot of interest in using this for like cleaning up oil spills. But so what's the challenge in terms of the environment of using something like a ferrofluid in that way?
One possible challenge with this is some of the magnetite nanoparticles might get into the environment, which could be pretty bad if that does happen.
So that is the challenge, is anytime you add anything, you don't know where it goes. The idea is if you can make them oily, they'll stay with the oil. Then so you have some good ways to potentially get rid of most of them. Can you tell us a little more about that?
Can you repeat the question?
The big challenge, anytime you add anything to clean something, you can do more damage than you do good by getting your cleaning agents into the environment. Okay, so in this case, your goal is to say, can we make the nanoparticles stay with the oily part? Then can you talk more about how you're going to remove all of that, the oil and the nanoparticles?
Using probably a large magnet, because the oil will bind with the nanoparticles in the ferrofluid. So a large magnet would collect both the oil and the ferrofluid.
Which is really easy in the lab and a little harder on an ocean.
Right, yes. Yeah.
What is your sort of one good hope in terms of the fact that they can potentially get into the environment? Fundamentally, what is magnetite?
Iron oxide.
And if you were going to like explain to your 5-year-old sibling what it was, what would you call it?
I don't really understand the question.
I'd go for a rock. So it is a natural just rock, literally. All the ites are rocks. So that's a good thing. It is actually a natural occurring mineral that you can find. And there's iron oxide pretty much everywhere. So those are positive aspects of sort of using it for environmental cleanup. Okay, so now I've given you guys all lots of time to think. Now other people get to ask a question.
So the way we made it was we used iron, FeCl2 and FeCl3, and we had solutions of both of those, and we mixed them together. Then we added ammonium hydroxide to start forming the magnetite itself, and then at a certain point we added oleic acid, which not only acted as to repel the water, but also it acts as a capping agent, which stops the nanoparticles from growing any larger.
Okay, so this is your, when you're talking about synthesis, here's your quick lesson. Okay, you said you use FeCl2 and FeCl3. What were they? What was their goal? Why'd you use them?
We needed the iron.
They're just a source of iron. So when you're saying something, we used FeCl2 and FeCl3 as a source of iron.
Yes.
And then used ammonium hydroxide as a source of?
I'm guessing oxygen, but I don't fully understand.
The hydroxide is OH, and it takes the oxygen from the hydroxide. So that's your source of oxygen to make iron oxide. And for everybody, when you give your syntheses, if you just say those extra few words, then your audience will have a way better understanding of why you did what you did.
Any last questions? And if not, then let's thank our group.